Hello, this is Joe Bacos welcoming you to this week's edition of the Taurus Report, where we will continue looking at the development of the history of cosmology and astrophysics. Last week we left off with Newton, and today we'll kind of go into Einstein a little bit. So today's episode is about what Einstein got right exactly and what Einstein got wrong. As we saw last week when we were discussing the first beginnings of cosmology with the Babylonians, and interestingly, they connected the motion of things across the night sky with the human heartbeat. So a heartbeat, they made 60 heartbeats, is 60 seconds. So a heartbeat essentially for the Babylonians was a second. And I don't know if most people are aware of that, like why it is that we have 60 to a minute and how that is connected to the heartbeat. It really was done that way by the Babylonians to track the motion of things across the heavens. So if you look at the position of a specific star, let's say, or a specific constellation, each night at exactly the same time every night. And you would watch how, over the course of time, at the same time every night, that constellation would appear a little bit further along than it was the night before. So interestingly, they equated one heartbeat or 1 second with 1 day of constellations moving across the night sky. And so everything to do with cosmology for the Babylonians was seeking to connect the clockwork of the heavens to the beating of the human heart in a very deep way, in a very intimate connection, connecting humanity to the cosmos. And so a lot of it was theological, and historically it is no surprise that many of the astronomers and astrologers and cosmologists, and early on astrophysics too, astrophysicists as well, were deeply religious or spiritual people. And I mean that sort of in a general sense, because astrology is like that too, seeking to make connections from the entire universe to the human being. And I think that many modern scientists, astrophysicists in particular, I'm sorry, but I think many of them, or perhaps most of them, are kind of boring people with no imagination, because they get deeply offended if you make any kind of religious statement or spiritual statement in regards to astrophysics or, observing the night sky. I mean, I understand how in this modern time with the scientific method, there's times when we're speaking scientifically and we want to speak strictly in terms of evidence. And that makes sense. I understand that. But there is something innately spiritual about, to me, contemplating the universe and where it all came from, and what is the ultimate purpose in life, all those kinds of questions. I think it's historically, you can see it's very natural that people think in those terms. And I'm not just talking about ordinary people or people who are primarily mystics. I'm talking about people like Leibniz or Newton or Einstein, or many people who approach these things in a scientific way. For them, it was not that much of a stretch or a contradiction to also think in spiritual or religious terms. And so, in my opinion, something is lost when we very strictly try to separate those kinds of things in the sense where we're not allowed to talk about one when we're talking about the other. Um, Again, when you're talking about making predictions and mathematical equations and proving and testing hypothesis and all of that, I understand that we don't want to submit mythology or feeling or emotion. We don't want to submit that as if it is evidence when we're talking about something in a scientific sense. But I don't think things need to be that strictly separated. And I don't like the fact that many modern astrophysicists just exhibit a sort of contempt to any sort of spirituality or religion. And that's just a personal taste. So, anyways, I seem to have digressed, and I want to bring it back now to what it was that Einstein was correct about, and why he came up with his equations, why he came up with his view of the universe in the sense of a space-time continuum, where he makes time as if it is sort of treated as if it is a continuum like another dimension of space. And how did that solve the problems he was working on? Why did he do that? And also explain why modern cosmology is so dependent upon that formulation and really is stubborn about looking at anything else, in my opinion, mistakenly. So let's look at that next. First, a little housekeeping. I would like to repeat that for all of these shows, all of the Taurus Report shows, I put the links to every website that I talk about. Often when I bring up a topic, I'll bring up a website that you can go to sort of look a little bit more in depth on that specific topic. And so links to all these sites will be in the comments for these videos. Now, a little bit of housekeeping. I do want to refer you again to my site. And you can get to that if you open up a browser and you type in Taurus Report. All as one word, Taurus Report, one word, no spaces, .com, and hit enter. Then you should either get to see a link or be able to get to my site, the Taurus Report. And on that site, you can find links to all of the videos. You can listen to them on Spotify, or you can see them on YouTube, or you can go to Facebook and see them. And then also is a link to my paper on cyclic gravity and cosmology. If you hit that, then a link to my paper on this comes up, 23-page paper explaining everything in detail. Now, to continue with what we were talking about, why did Einstein's formulation, why did that catch on? And it all starts with what's called the Michelson-Morely experiment. And here's the idea with the Michelson-Morely experiment. It is simply this. This is a schematic. And so you have a light source that is on a moving object, like let's say a train or something. And I'm sort of oversimplifying for those of you who know the details of the experiment in depth. I'm kind of oversimplifying just to give the major idea for a layperson so they kind of understand what's going on. So I'm oversimplifying, but this is the basics of it. So you have this light source. It's on a railroad track, right? And it emits two beams. So one beam goes to a mirror that is also moving. It's also on the train. So this mirror straight ahead is moving along with the train. Okay? So a light is shown and it hits that mirror and comes back. Now, also moving along with the train is another mirror off to the side where a light is shown. And since that mirror is moving along with the train, both mirrors are moving along with the train, then the light would go to that one perpendicular and hit the mirror and come back. And they wanted to compare the timing of those two light sources coming back. And what is the point of all this? I mean, why do they want to compare these two, right? So you've got you're traveling on a train, you've got some mirrors straight ahead of you, you shine a light to it, the light comes back, and you want to see how long did that take, right? Then there's a mirror that's traveling along with you, but kind of off to the side somewhere, right? And you shine a mirror to that, shine a light to that mirror, traveling with you, and the light hits that mirror and comes back. And you want to compare the timing of those two beams. So when they arrive, you want to compare the timing. Now, why would they do that? What are they trying to prove? What's the point? And it comes back to this question of light as a wave. At that time, theorists were wondering, okay, well, we know that light's a wave. There's other experiments demonstrating that, which I'm not going to get into. So let's just say they found out that light's a wave. Well, whenever you have a wave, you need some sort of medium for that wave to be traveling in. For instance, you see a wave on a lake, right? The medium is the water. So the wave isn't any particular piece of water, right? It's bits of water molecules moving in an organized way that create the wave. And so when the wave travels across the lake, the medium is the water. If you have sound waves, that you're hearing this, you're hearing me speaking right now. So those sound waves, there's waves moving in the air. So you always have some kind of medium. And when theorists first found that light was a wave, the natural sort of question they're asking is, if light is a wave, then what is the medium that is carrying it? They called that medium the luminiferous ether, or the ether for short. And they wanted to know what it was, what is it made of, how does it behave, how does light travel in this ether. And so they had all these different experiments trying to detect it. And so the idea was that it was very difficult to detect, and if you're moving through space, if you are moving through space, and we'll say relative to the ether, which means that theorists assumed that whatever the ether was, it was at rest in the universe, and all motion that we saw could be related to the objective rest frame of the ether. So if you're moving, true motion, objective motion, could be measured relative to the ether if we could discover this ether. And so that was the point of shining a light on this moving train. Because if there was an ether, then you would assume that the light beam shown to the mirror straight ahead of you, because you're also moving in that direction, when it reflects back, that light should arrive before the light that was shown to the mirror off to the side, right? If you're moving relative to the ether. And so they tried to move relative to this ether, and they thought that this experiment would prove that the ether exists. Right? Because if you found that this light beam arrived first, if it came back to you first, so again, here's the idea, as I shared earlier. Let's move this mouse a little bit here. Well, it doesn't want to stay, whatever. So anyway, so if you're on this train and you're shining a light straight ahead to a mirror that's moving along with you, and that's going to come back and reflect back to you, and I'm moving relative to the ether, and then I shine another light that way, and it reflects off a mirror also moving with me, and it comes back to me. If there was an ether, you would expect that this one would come back to me first, right? Because I'm traveling in that direction. So even though the mirror is also traveling, right, it's going to reflect off that mirror in front, and it's going to come back to my detector, and it should arrive first before that other one does. Even though the distances to the two mirrors are the same, in this one, I'm moving in the direction of the light that's coming back to me, so it should arrive first. So what were the results? What were the results of the experiment? Now, the results of the experiment were that they both arrived back at the same time. And no one could figure this out. Okay, if they arrived back at the same time, how is that possible? How is it possible that the light should arrive back at the same time? So no one could make sense of this. It sort of was saying that there is no ether. Not only that, but even more so, as they did more and more of these kinds of experiments, they found that basically in a vacuum, no matter how fast you're going, any light that you measure in whatever frame of reference you're at always had the same speed in a vacuum, which seemed very strange, because if there was a medium that is carrying the light, right, if you travel faster in that frame of reference, then you would expect that the light would be traveling slower. And they never found that. They always found that no matter how fast I'm going, light seems to be traveling with the speed of light, no matter which reference frame I'm in. And so this created all kinds of problems that ultimately Einstein solved these problems using what is called non-Euclidean geometry. And so we're going to look at Einstein's solution to all this next. So another little bit of a digression that maybe I should have brought up earlier, and it has to do with the speed of light. So keep in mind the difficulty of the problem of the Michelson-Morely experiment, which was an attempt to find the medium through which light travels. But before the Michelson-Morley experiment, or you know what, about the same time, I'm not sure when Maxwell came out with his equations about the speed of light, but Maxwell predicted that what the speed of light was, and it was found that he was right, and he also predicted something strange about the behavior. Okay, so Maxwell predicted that the speed of light always in a vacuum had to be 186,000 meters per second, right? And he predicted that, and he said that must always be its speed, and that must always be its speed relative to anyone or anything, which is sort of weird. Okay, now we're not used to that kind of thing in our day-to-day experience, where something has the same speed relative to anyone or anything. We're just not used to that sort of thing. So, what do I mean by that? Okay, let's use a train again. So, train's traveling 60 miles an hour. Well, let's suppose I was like the Bionic Man or something, and I can run as fast as a train, which has always been a fantasy of mine. But anyways, so if I start running to catch up with the train, well, as I catch up, the train appears to be moving slower and slower, right, as you catch up to it. If you're traveling the same speed as the train, right, then relative to you, the train would be going zero if you're traveling the same speed in the same direction. And that's just our day-to-day experience. It's a type of relativity in that sense that we're all used to when you talk about relative speeds. If you match the speed of something, then relative to you, that thing is traveling at zero speed. If you're traveling along at the same speed, you don't seem to be moving relative to each other. So that's a form of relativity that we're all used to. Well, it was Maxwell that came up with the equations demonstrating why light must have the speed that it does. and also demonstrating that in relationship to anyone at any time, no matter what speed they're traveling, light must have that speed. And we're not really used to this kind of thing, although we sort of can experience the weirdness of it. There is one context in which we can, in our day-to-day lives, sort of experience this. And I want to mention it now because we're going to come back to it later. And that is electromagnetism. So if a charge is moving, it produces a magnetic field. But if a charge is at rest, it does not produce a magnetic field. But what about the weird situation where, just like I was talking about running alongside a train, what if I'm running alongside an electric charge? So Maxwell's equations say that if that charge is moving, it will produce a magnetic field. And if the charge is at rest, it will not produce a magnetic field. Well, what if I'm traveling along with it? Am I going to detect a magnetic field? And the answer is no, which is sort of weird. Because let's suppose we run by my friend who's standing still. As I run by, I can yell to him, "Hey, are you detecting a magnetic field from this charge that's traveling along with me?" And he'll say, "Yeah, it has a very strong field because you're both moving very fast." And everybody knows if an electric charge is moving, it produces a magnetic field. And then I'll look at like my little compass I've got with me to see if there's a magnetic field coming from that charge. My compass says no. And I say, "I can't detect any field." And he says, "Well, it's there." Okay, and so is the magnetic field there or it's not? Okay. And all of this is demonstrated by Maxwell's equations. And so there was a great deal of weirdness going on that theorists could not really wrap their heads around. So there was that problem with picturing the speed of light the same to all observers, which was very weird. The fact that a magnetic field, one person might say it exists, and another person might say it doesn't exist. Okay? And for that matter, electric current is the same way, right? Electric current just means a charge moving. Well, if I'm traveling along with a charge, is there a current? No, because the electrons are at rest relative to me. So relative to me, there's no current. If I'm moving along with them, I don't see any current. Okay, so all of this causes the mind to have, various problems imagining things. But that difficulty with the magnetic field, we can see that in our day-to-day lives. As far as two people either detecting or not detecting a magnetic field. Then let us bring all of this together. So, two things we've been discussing, both of them creating mental problems for us. One was the Michelson-Morely experiment. What is the medium that is carrying light? Okay, that one creates mental problems. And then the other one is, how can the speed of light be constant in all reference frames? Like, even if you're moving along with it, the speed of light has always the same constant speed. No matter how you're moving or what direction you're moving, light seems to have the same constant speed. Well, Einstein, with his non-Euclidean geometry and linking up time as if it is a fourth dimension of space, was able to solve both problems at once. And this is why his theory gained immediate recognition as something interesting, even if people didn't really believe it to start with. Everyone said it was at least interesting. Okay, and so what did he do? So first, he dispensed altogether with a medium for light. And he said light is a wave-like variation of the electromagnetic force, and it doesn't have a medium. And so we get rid of the ether altogether, and we just say light varies like this, and there is no medium that it travels in. So the ether, gone. Then he said that any object in relative motion contracts in the direction of motion, but not just that object. Not just that object, and this is key. All of space for that object in motion contracts in the direction of motion. So, coming back to the Michelson-Morely experiment, what does that mean about this experiment? If the detector, and remember, we're talking about the train here, right? If the train is traveling in this direction, the train is traveling to the right. If the entire train gets compressed in that direction, not only the train, but all of space, right? 4 people on the train, all of space gets compressed in the direction of travel. If that is true, then it explains why the light coming from the reflector, ends up arriving at the same time as the light coming perpendicular. And it seems like, you know what, I apologize, I may have misspoke earlier in the program. All right, so I'm realizing I made a mistake early, so forgive me. Earlier I said that when we did this perpendicular light experiment, we were expecting for the light in the forward direction to arrive first. And in fact, I was mistaken. The people who set up the experiment, they were expecting the light going perpendicular to arrive first, because the mirror that I'm reflecting to in the forward direction is traveling away from me, because it is also on the train. Okay. And so they were expecting the light from the perpendicular direction to arrive first. That's what they're expecting. And so I misspoke. So going back to that, sorry about that little mistake. But anyways, going back to that, because Einstein, according to his theory, all of space in the direction of travel becomes compressed relative to your speed. So if you travel faster, then the universe becomes more compressed in that direction. Because it gets compressed, that means that the light does not have as far a distance to travel, and so it can arrive synchronous at the same time as the light that has reflected off the perpendicular reflector, because it has a shorter distance to travel. And so he was able, by making this claim, he was able to explain the results of the Michelson-Morely experiment. Now also, at the same time, another aspect of his non-Euclidean geometry meant that he was able to explain the contradiction caused by Maxwell's equations, where Maxwell is saying that in all reference frames, the speed of light in a vacuum has to have this same speed. It has to be constant, no matter how you're traveling. So Einstein was able to solve that by saying, with motion, for an object that is moving, time slows down. And so this is special relativity. It does 2 things at once. First, anything traveling at a velocity, all of space for that object becomes compressed in the direction of travel. Secondly, for any object in motion, time slows down. So because time slows down, if you're in motion, then it makes sense that even though you're catching up to light, let's say you're traveling along with a light beam, right, and you're catching up with it, normally when we're catching up to the same speed as something else, right, the thing appears to be traveling slower to us. But with light, it's different, because as you're catching up to that speed, according to Einstein, time slows down for you, right? So as you catch up, light seems to be traveling faster because time is slowing down for you. And so by doing this, he was able to solve two things at once. Now, him being able to solve two things at once meant that his idea was preferred to the idea of Lorentz because Lorentz was working on a solution to the Michelson-Morely experiment as well. And this is the interesting thing. In my opinion, Lorentz was correct and Einstein was wrong. And in my opinion, we're going to go back to the formulation that Lorentz was working on, and it never really got into finished form because Einstein's theory, having the success it did explaining a lot of different things at once, was preferred. And so sort of Lorentz's view is sort of set aside, but I think we're going to end up coming back to that. And what do I mean by that? So what I mean is this. Lorentz and others, there was some other theorists, I forget the names now, I'm sorry, but Lorentz and others were reasoning that since we see this weird behavior of the magnetic field, as I was just discussing, that the existence of the field sort of depends on your reference frame. I mean, some people might say there is a magnetic field, and other people, if they're moving and along with the charges, would say, no, there's not a magnetic field. So Lorentz and others were thinking that the Michelson-Morely experiment could be explained if not the entire universe is compressed in the direction of travel, right? But only the object itself. In other words, if a train is traveling with all this equipment that we're discussing, if it's traveling in a certain direction, if that entire train is compressed in the direction of travel, then the results of the experiment would line up with what was found. And so they were saying that the train itself compresses, not the entire universe. And why does the train itself compress? And in this sense, there is hope to be able to explain that by known physical mechanisms rather than non-Euclidean geometry, because with electromagnetism, forces increase with speed. And so it would make sense that there may be some sort of interaction with a moving object with some sort of ether, or even the ether might even be thought of is the average velocities of all the surrounding medium of objects, atoms, particles, subatomic particles, all of that. Even in empty space, there's trillions of them, okay? And so an object at velocity having interaction with all of that, and possibly with some sort of ether. I think an ether might come back as cold neutrons, not neutrons, cold neutrinos. But I'll get to that in a later program. But my point is, there was some possibility or some sort of suspicion that there may be a physical mechanism explaining why an object at velocity would become shortened in the direction of travel, and also that approaching the whole thing in this way would mean that there is some sort of universal rest frame, which I believe in, and I explain that in my paper. But this was Lorentz's approach to it. Now, Einstein did not approach it that way. He went the route of non-Euclidean geometry, which means that for an object at velocity, all of space gets compressed in the direction of travel. Now, in my opinion, this leads to obvious logical contradictions. And the first one that's very obvious is that if you're going to say that all of space becomes compressed in the direction of travel, well, What about for people not traveling at that velocity? Well, for them, that space is not compressed, or it's compressed in a different way. Okay, so how can all of space be compressed because of the travel of this person, whereas for another person, all of space is not compressed? And the answer that Einstein gave, and standard theorists have given ever since, is that these things are relative, and they mean it relative in a new sense of the word relative. And it is my opinion that this sense of relativity is not what most people mean or understand by relativity. And what they mean by it is, in my opinion, the contradiction's okay. In other words, it's okay to say that space and time are relative to the velocity of the observer. So, space and time for this person are different than space and time for this person. And so each of them, space and time, are defined differently depending on their moving reference frame. Now, I think that's a logical contradiction. Standard theorists insist it is not a logical contradiction, and they invoke various things like perspective. They say something like, if you look at a very distant mountain, it looks like it's only as tall as your thumb, and you get closer and it seems taller. And so they try to explain it in terms like that. And the problem with all type of explanations like that is that, yes, but the mountain does have an actual height, and it makes sense from the sense of perspective that it would appear different to different people. But there is an underlying physical grasp of why the appearance is different. And so trying to explain what Einstein means by relativity by the use of that type of analogy, to me, is unconvincing. I don't think it's convincing. And so, in my opinion, then, what did Einstein succeed in doing? What he succeeded in doing was, in terms of what we've discussed so far today, he was able to explain time dilation, the results of the Michelson-Morely experiment, the showing why Maxwell's declaration about the universality of the speed of light, why it works. So Einstein, in his formulation, was able to make all that work. Now, Lorentz's formulation couldn't explain why light would have this same apparent velocity in all reference frames. Maxwell's formulation could not explain it. Now, he was working on it and coming at it from the perspective of electromagnetism. And as I said, I think that his approach ultimately is going to be shown to be the correct one, and Einstein's is going to be shown to be wrong. And thus far, we've only discussed special relativity. And so you have special relativity, you've got general relativity. And what is the difference between the two? So special relativity has to do with time dilation regarding motion. Now, general relativity incorporates also the fact of, well, I call it increase of mass, which is not strictly speaking correct. Oftentimes I fall into that sort of shorthand. An object in motion has a larger mass. And the correct way to say that is to say an unexpectedly larger momentum than it should have. So if you hear me interchangeably use those two phrases, forgive me for being a little bit inaccurate. But for a layperson, that's kind of how they picture it. So an object in relativistic motion has a greater mass than the object at rest. And general relativity explains that. And it also explains the time dilation in a gravity well. Okay, the fact that gravity, a high gravity, causes time to slow down as well. And so, in our next episode, what we're going to look at is general relativity. Now, I had sort of promised, and I apologize, I was going to say in this video why I think Einstein's wrong and how do I explain all these things in a different way. And instead, I don't really think I am able to do that until I delve into general relativity as well, because all of it has to be approached and dealt with kind of simultaneously, which I am going to do in the next episode. So in the next episode, we will look at all of this stuff in terms of Einstein's special relativity, Einstein's general relativity, and then I will explain why it is all mistaken. Einstein's approach using non-Euclidean geometry to solve all that. Why does that work to make very good predictions about time dilation and increase of mass, and also deflection of light? Okay, so there's several things where Einstein's formulation makes excellent predictions and agrees with experimental data. And so I have to show, and I will show, why Einstein's formulation works to do all of those things, but also why it is wrong. And it fails to explain some other things, and why a new formulation using cyclic cosmology and gravity will work to explain both the things that Einstein's theories do and also the things that Einstein's theories do not explain. And so I hope you'll join me next week for the next episode of the Taurus Report, and you all have a wonderful week. Bye-bye for now.